Good. All right, thanks everyone for coming. I'm Will Goff. I'm the president of NES-Optica this year. Josh, would you introduce yourself?
Hi, my name is Josh Brown. I'm the treasurer of NES-Optica.
Jason was unable to make it, unfortunately, our secretary, because of traffic. Before we get started, I just wanted to have a quick thank you to Steve Antone for hosting us here at Opticos. Invite him up for a couple words.
Listen, we really welcome everyone here tonight. Local sections are the gateway drug to the optical community. You know, most of us got introduced to the Optical Society, now Optica, by going to a local section activity, either at university or an event like this. This is the heart of really the true optical community. I look here and I see people that I have known for decades, too many decades perhaps. But what's also nice is to see that there are new faces here tonight. And I think that's one of the things we can all work on, is making sure that we extend to the younger people that are in the community the invitation to come to these kinds of meetings. When I started, I was at Polaroid. Meetings were all held at iTech. It was sort of a scary place to go to. You know, iTech was a sort of a pantheon of optical technology. You went into a guard's desk. It was very intimidating even for me. But what I found there was a very welcoming community that really seeks to build upon itself and bring in as a diverse a crowd as we can. So I want to thank everybody for coming tonight. It's a privilege to be able to host these. This is the 75th year. I have here the program from the 50th anniversary, which is dated in May of 1999. On it, it lists the founding members, and you know, this particular section has a really inspirational legacy to it, with people like Walter Baird from Baird Atomic, Edwin Land, and many others that became, forget the pun, luminaries of the field. So I just want to welcome everybody and say we hope to see you at future meetings, and encourage everyone to go hard on the speaker tonight. And this is your chance to ask any question that you want, and he's a delightful person and very accessible with questions and answers. So again, thank you for coming. I forgot the most important part. I want to thank Mara and Brianna for really putting on this event. You know, it's great to be able to get up here and speak, but the people that really make this happen are people like Brianna and like Mara, that make us look good at here and at trade shows and at all of the marketing things that we do. They're a key part of what we call the Opticos experience and what people have when they do come here. So again, thank you, and we look forward to a great evening. And I just want to also thank the other Opticos employees that are here to help support the community. So thank you.
Thank you, Steve. So as part of our last event for our calendar year, we wanted to do a update on the Optica group, the local section group from the council. So just as a recap for the 23-24 year, we had 9 hybrid meetings at 4 different locations. So thank you again for all of our hosts and all of our speakers for all of those meetings. Our meeting attendance, again, these were hybrid, held both in person and on Zoom, and in total, we averaged about 39 event registrations per event. We had a pretty awesome array of speakers, ranging everything from industry and fairly, you know, consumer-based applications to R&D and kind of bigger picture research applications. So it was a really great year for all of the talks.
We also have been working on our outreach portfolio. During the pandemic, we unfortunately had to step back from doing outreach, but that's back and in full swing. And we're really excited to fill the calendar with outreach events again. Now, these outreach events don't happen without your participation. We need volunteers and we need people who are enthusiastic and engaged in talking to kids and sharing our love of optics with the local communities. There are events all the time. We only participated in 3 this year, but there are more that we could be participating in if there are more volunteers who want to help out and come out to events. The next event we have is Saturday, June 1st. It's the Boston Citywide STEAM Festival. We'd love to see you there. Please sign up on the website if you're interested. And I'd also like to shout out to Bruce Miller, who's I don't think here tonight, but a member of the optics community, for a huge donation of optics supplies to that outreach portfolio. So thank you. Sure. Another part of being an organization is we have to give an annual financial update. And the good news is we're in a financially strong position. Thank you very much for your continued sponsorship for all of our corporate and professional sponsors. We're in a very good financial position going into our 75th anniversary celebration year. And we're hoping to have a nice event in the fall to commemorate 75 years of serving the local community. Our assets have grown over the year. We're continuing to bring in membership dues and income from all of our various events that we've been having. And I think we're in a good position as an organization to continue serving for another 75 years.
If you aren't already, we welcome you to become a member or renew your membership. I think also this year, do you want to talk about the renewal?
Yeah, sure.
Just the timing of that.
Yep. So when we set up the new website and the new membership and registration system, we grandfathered in anyone who was a member or had been a member in the last few years with a free year of membership to get you incentivized to get into the system. This year, membership renewals will all come due about the same time in September when our year kicks off. And at that point, you'll be getting emails from Club Express asking you to renew your membership. We will probably continue charging dues for the year, but I think one of the things we'll talk about as a council is whether dues make sense or whether we just want to get people to sign up. So take a look out for emails prompting you to sign up, and please do continue your membership. Or if you're not a member or want to be a member, go to our website, NES-Optica.org, to join up.
And even if there's a fee right now, you will make your money back if you're also an Optica National Society or International Society membership. Yes. Yeah, basically you'll get a discount with that sign up.
And most importantly, you'll get a discount on dinner registrations.
Also that. Looking ahead to next year, so one of the biggest things is we're starting to plan this 75th anniversary celebration. Actually, we've been planning it for a while. So we're finalizing the details on that, but our plan for right now is for it to be in September. So as soon as some of that is announced, we'll definitely let everyone know. That September is when the meetings will start again. And right now we have voting open for next year's council. So the people listed here, a couple of returning members, as well as a couple of new members, are all candidates that are open on the council. So the way this works is there are 9 positions open on the council. We currently have 8 council candidates. So hopefully they all make it in unless someone votes against them. But please just take a second to go look online and just kind of get to know some of the new oncoming council members or perspectives.
And if you are interested in being a member with more influence, or you want to also be on the council, I think we'd still be interested in having that 9th councilor. Just looking around, there's some faces who are consistent participants who I know would be a great member of the council for next year.
May I ask a question?
Sure.
At the 50th anniversary celebration, we make it a time capsule to be opened at the 75th anniversary celebration. Does anyone know if there
We'll look into that.
Oh. You know where it is? Who has it?
Andy Bodkin.
Okay.
Oh,
So now you guys know.
Okay.
You gotta get that for the.
Did not know about that. Thank you.
and I think that means that we need to make one for the 100th
Yes.
too. All right.
All right, and thank you again to our members this year, and particularly the outgoing council members, Hillary, Andromeda, and Phil. Some of them involved in. Yeah. Some of them have been involved for some time, beyond even just last year. So thank you again for all guys, your guys' help. Also some previous council members who are providing a lot of support, particularly as new council members are coming on. Peter Clark, who I think I saw here, thank you, as well as coming to many of the outreach events, and Gregory. And also, of course, thank you to David Lees for his continued support and always finding these amazing speakers. Thank you so much. Last but not least, special thanks to all of our industry sponsors. We couldn't really do a lot of the events that we want to do without your support, and we appreciate both your support and a lot of the attendance that you guys come to a lot of these events. So thank you very much for that support, and both financial and being here in person. All right. Finally, tonight's talk will be from Professor Supriya Chakrabarty. Professor Chakrabarty is currently the director of the Lowell Center for Space Science and Technology. He received his undergraduate degree from the University of Calcutta and his PhD from the University of California at Berkeley. As part of his PhD dissertation, he built a sounding rocket payload containing 5 grazing incident extreme ultraviolet instruments to study the aurora, participated in the development of the EUV-FUV spectrograph flow aboard the U.S. Air Force STP-78-1 satellite for upper atmosphere and ionospheric studies, and analyzed data from the Apollo-Soyuz test project in terms of plasmaspheric helium-ion distribution. Mouthful. His research interests include direct imaging of exoplanetary environments, upper atmospheric remote sensing, using visible to ultraviolet hyperspectral imagery from ground and space platforms, and full waveform near IR LiDAR instrumentation for characterization of forest structures. He has supervised 12 PhD students, edited or guest edited 9 books and conference proceedings, published over 200 articles, and was awarded the 2016 George W. Goddard Award by the Society of Photonic Optical Instrumentation Engineers, or SPIE. So, Professor Chakrabarty, I'd like to invite you up, and thank you for coming.
That Apollo-Soyuz reference makes me, feel older than the oldest person in this room. So thank you.
Just a second.
And I'm also very surprised you fed me before before I spoke, so I could just leave and I'll be ahead. Right, Josh, thank you. I got to know Josh when he spent some time in our lab. So what I'm going to tell you about is our work. In fact, there are smart people like Josh and others in the lab who do the hard work. I take credit and get fed. So that's my job. And what you are seeing is a balloon flight. And these are the balloons that have been in the news for not so good reasons. And those balloons were at about 40,000 feet high. This is 120,000 feet, about 40 kilometers. I was getting confused with the unit. And this payload and other stuff weighs about 6,000 pounds. So we're flying a real astronomical observatory in space. And all the things that you need to do for astronomy, that's in here. So and in this thing, my only contribution is that sticker. It wasn't there. So let's start with some questions. What we're trying to do is exoplanets imaging. 10 years ago, I used to say, how many planets are there? But I know you all know that answer. But I'll ask a question about how bright is our largest planet in visible light compared to the sun. So how bright is Jupiter? If you are a space alien, if you're trying to take a picture of back at the sun and the solar system, how bright would Jupiter be in visible light compared to the sun? The answer is
10 to the 10, 28 minutes.
yeah, you're close, about 26th or something. So, but it's about 1 billion times. The largest planet is 1 billion times dimmer than the star. And now the nearest star is about 3 light years away. So, so you can imagine the distance between the planet and the star is almost right on top of one another, roughly a fraction of an arc-second. So the challenge that anyone is trying to do this thing in visible light, you're trying to measure the reflected light, and where you don't care about the light of the star, and you're trying to image the planet. So what you have to do is, those of you who have kids or grandkids, the opening scene in Harry Potter movie, Dumbledore walking around with turning off the street lights, called the deluminator. So this thing, heart of this instrument is a deluminator. And what we do is try to dim the light of the star without doing anything that light does to the environment. That's the challenge. And I'll show you what we have done, but I'll give you a punchline, which is where I need to brag about our team. There are many fine instruments that have been built and tested in the lab. Our group is the only one in the world who has actually flown things like this. So we have flown 4 times, twice on rockets that go up and come down 10, 15, 20 minutes later, and twice on balloons. So I'll tell you about that. So because I'm going to give you that story, I'll start with the history, how we started. Now, only if I knew how to use the, okay, thanks. So it started with this simple question, and it's in 2003. By that time, there were about the existence of about 50 or so exoplanets were known. And they were known because as the planet goes around a star, it wobbles a little bit. So you could measure that Doppler shift or the periodic shift, or sometimes a little later, when a star goes in front of it, like an eclipse, it dims the light of the star a little bit. So those indirect methods gave us an idea that there are planets around these stars. So it started with this question: is there even one of those 50 that we could image directly? And so what everybody does, and we did that too, is went to the library and tried to find if somebody has done even any theoretical work. So this is a paper that came out in SPIE, and there was all kinds of stuff, but this is the equation. And I'm not going to talk about equations, but the sentence after that talks about what you could do. It says, note the strong dependence on the planetary separation, which makes sense. If the planet is far away, even if it's dimmer, we could measure it. Hubble measures much fainter things than the planets. So we could do that. And what it says is that Jupiter's analog at 2 astronomical units separated from the parent star can be detected with a 1.5 meter telescope. It's in that equation, with 5 sigma confidence in less than a minute. And in those days, all we did was sounding rockets. We built things that go up, collect data for about 5 minutes, come down. So we said, well, we can multiply this parameter by that and take something else out. And it looks like in 5 minutes, if that thing is correct, we should be able to do that. Well, so what we did was we write a proposal to NASA, and these are the pages. I'm not going to describe this, but the contribution that, again, I came up with is the name of the project. I demanded that it had to be a pronounceable acronym. And so the planet imaging concept testbed using a rocket experiment But when we changed to balloon, then rocket became recoverable. So, and then we have built something, picture A, picture B, and picture C is what I'm going to tell you about. Picture and picture B are the two rocket ones. And as we pointed out, that, what we're trying to do is develop technology and validate them. That's what we're doing. And so some other things that we had talked about when we could, it'll be available on the sky for us to see. And, it was so simple in those days, planet and star contrast was about 10 to the 8. We're told that you could do some math, and all you needed was 1,000,000 to 1 contrast. And this term, I want you to know, contrast is how bright the planet is divided by the brightness of the star. And so, and it's expressed in a fraction. So that's, and this was our sort of design, 2003, pretty high tech for that. Then we realized how naive we were. This is a design of the heart of this thing. It's called a Visible Nulling Coronagraph. And this was originally developed at JPL. And we talked to them and said, hey, you're doing these things, would you like to fly? And so, we waited, till about a month or two before the proposals were due, because otherwise they would have taken the idea and flown it. But anyway, what it says is, it's we needed to do only about a 10 to the minus 6 contrast. So that was what we had to do. And so we're fortunate that we're selected. And there were stuff that we had to do, all kinds of sort of war stories, one thing after another. And Dan was involved with us on this project for a while. When we're doing the rocket. So, in our research group, we do everything ourselves. We build, rockets are where, you try to design and build, and then a lot of uses of files where things don't quite fit. And so, I'm sure, you have, those of you who have done it, but when we're ready to fly, we heard that a group at NASA Goddard has a 0.5 meter diameter primary mirror that was built by Kodak, and it weighs only about 5 kilograms, so extremely lightweight mirror. And so they said, would you like to fly this thing? And we said, sure. And then there was, side bets going on, which I didn't know whether, when would it break, whether when we launch it or when we come down. So this was going on. And so this is the rocket design from change dramatically from that. It's a carbon fiber optical bench, a little titanium structure where we have the secondary mirror, the primary sits there. And this mirror would not have fit in the standard NASA fairing. So we had to go beg and make, appeal to them. So that's why it's a little, little tapered version. It's a wide where the primary sits. And so this is what it looks like. And the other thing is, the way NASA launches it, the telescope is pointing at the ground. And underneath are the boosters. So all the rocket motors are underneath. On top goes other rocket structures. I'll tell you about that. And this is what the full blown thing looks like. So this is our payload, nose cone. This is, and between goes in a pointing system, a parachute, the entire recovery system, and all of those things are in there. And the reason we could even dare to try to do this was NASA, we worked with NASA to develop a pointing mechanism, which was, they used to have cold gas jets coming out, but, even the valve could send this, vibrate the entire structure that would not keep our alignment. So we worked with them to have 2 gas jets going in opposite direction, and we'll change the irises. And by differencing, we could point things carefully. And that pointing mechanism that we developed in there led to something that could point at a star while the rocket is moving ballistically. And first we started this way, we go up, point at the star, and then point another to know which star we want to go to, and then we're going ballistically. And while it's doing it, they could hold that pointing to about 1 arcsecond with this. So that is, it's a great collaboration. The way we work is, we're sort of at one team. So this is what the experiment looks like. This is again where the primary mirror sits. These are all the part towards the nose cone, and the other side goes gets the boosters. And if we take out the skin and all of those, these are the three separate areas. We have a telescope. We have an area that we call the instrument, but this is where the Nulling Coronagraph sits, and then all the electronics that goes in there, detectors and others. And these are the two grad students who did the work. Chris Mandillo, Brian Hicks, you worked with Chris, right? And this is sitting on a shake table. So before you launch, you got to qualify to see, if it's space worthy. And here, these are ballistic missiles, right? So the first stage is usually very old, so old that it's not reliable for military use. So they give it to NASA. And so there is no guarantee that things will work. So it's a rough ride, but again, we're very fortunate that we had students who are very dedicated. We call them rocket mode. So nights, weekends, they all sort of mixed together. But so our first flight, what happened was about 70 seconds after launch, we lost telemetry. And all this 5 years of work, no data. However, we recovered it. And so this is how it came down, and you go on a Huey helicopter, pick it up and bring it back. But by the time you pick it up, you hear all kinds of rattling. And instead of one primary mirror, there were thousands of primary mirrors that we brought back. Such is life, and it's extremely lightweight. And that's when I got to meet Dan. Zynetics or Northrop Grumman at that time were getting into the silicon carbide mirrors. And their densities is a little higher than the lightweight mirror that we had. This was glass. So this is the flight 2 of this, and we have the usual measurements and stuff. But again, we put it together, and Zynetics were kind enough to make it to the same prescription of the glass mirror that we flew. And it's a Cassegrain. Actually, it's not a Cassegrain, it's a Gregorian, so that's where the prime focus is. And so we could put a stop in there. And we can talk about the details of the coronagraph here later. Well, not later, just now I'll do it. And so we're putting it together in our lab. And so this system is the Nulling Coronagraph. We take the light from the primary of the telescope and put a dichroic here, take the blue part of the light for even finer pointing that we need. So NASA points us to an arcsecond. We need to get down to close to milliarcsecond level to do any of the work. So that's where we use our tip tilt mirror to get the fine pointing. And then there are all these things that say you take one image and put a shear in it and then interfere it on each, and that's how you get the science. But we also to get the there is a calibration interferometer as well in here. And there are a couple other things. We have this DM is a deformable mirrors. These are individual mirrors. There are about 1,000 of them. And so you correct the wavefront using tip, tilt, or piston on those. So this is a mirror that there are many different types of deformable mirrors. In this particular case, there's a continuous membrane, and then there are other piston things that are, for each pixel, there are 3 of those that gives you changes the waveform. So we do that. There are others, and Zynetics has a piezo driven thing. And in here, this whole thing sits on 2 pieces of ultra low expansion glass, so ULE. And so you take one, the bottom one is the optical bench, it's about 1 inch thick. We glue all the components together and then align, and then then fire the UV gun to make sure there are no, and then put another one on top. So together, by putting those, it becomes a monolithic optical system. And that has roughly about 30 or so individual optical elements. And so the idea is when the rocket goes up and we start collecting data, we have no time to make any in-flight adjustments. We start collecting data above 150 kilometers, and the rocket stays above that for roughly about 5 to 7 minutes. So that's what we're trying to do, all these years worth of data for that 5 to 7 minutes. But nonetheless, it worked. So I'll show you what kind of things we achieved. Going backwards. So we had this roadmap. We had 2 of the sounding rocket flights, and then 2 balloon flights. And these are the years when we're supposed to fly. So the rockets flew in 2011 and 2015. And then again, the NASA proposals are roughly about 3 years or 5 years long. We ask, when we're delayed, we ask for a little more money to stay alive. And so then for our balloon, we got a 5-year grant. So let me show you what the rocket, these 2 flights achieved. So these are the things that we talked about, the 32 by 32, which is this almost 1,000 element deformable mirrors. We had a CCD detector. And one of the first things that we did was we demonstrated fine pointing from this rocket while it's flying. And so these are individual pointing. If you look at the RMS, we got down to 5 milliarcsecond. It's never been done before from a rocket. That's the still probably is the record. We also flew an Ethernet. There is an experiment controller. Each detector has a computer. All of those are talking in Ethernet for those 5 minutes. Again, nobody flew an Ethernet in there. And this deformable mirror, we demonstrated in space. People have done those things in the lab. Even though we did not get any real data during the first flight, but during the second flight, we did all of those. And we did some active wavefront sensing. So that's what we did in our 2 flights of the rocket. And this is a photo of the door that covers the rocket. So anything I didn't say or you have questions about?
You can get data back on once you get to cover the rocket. Is that your data stored?
No, the rocket itself has a transmitter, so it's sending us data live. So we got the data, and it stores it also. So we could get that back, but we can get the data, and it's low rate compared to other standards. You get 10 megabits a second. And that's good for most.
How are you measuring waveform distortion and feedback?
See, we're looking at A star. Field of view is very small, so there is, essentially A star. But there are multi-stage. The rocket NASA part, when they get us to about 1 arc second pointing, they have I think about 4-inch diameter telescope feeding a detector. So, and they could go down to about 6th magnitude star, and they look at the star field and get us to that. And so that gives us the first part, and then we do, as I said, I take the light from this telescope for our part. We only take the blue part of the light and then use that to do real-time active pointing. The red part goes for our science data.
Very basic and candid question, but why do you put a small telescope suborbital? Because you can have like large telescope on Earth and all doing the same job.
Yeah, people have been trying when we did and still today. The record, the best contrast that people have done, even with a 10 meter or whatever, is 10⁻⁶. What we're doing here is not do this, but we're trying to demonstrate all the other things you need for future space missions. Many, other things, you guys all pay taxes, would you let me fly a thing that's, a couple $2 billion without knowing all the technology is ready? So what we're doing is maturing the technology for prime time.
Yes, and that's suborbital, right?
This is suborbital, goes up and come down. Both of the things that we're doing is,
Before the atmosphere.
no.
It goes in space?
The rockets are above. I mean,
Okay.
the apogee of the rockets are roughly about, because we recover it, they go up to about 250 or so kilometers apogee. And we launch from Fort Sumner, New Mexico, and it comes in back in the desert. It could go up higher, but there is no guarantee it'll come back in one piece.
Why do you put AO in it?
Why do I put AO on it? It's the distortion of the optics,
Okay.
not the atmosphere, the optics. And then, when we fly things in space, there'll be thermal distortion, all of those things you have to correct, Your launch will misalign things. So you have to.
So why so many actuators on the DM?
I'm sorry.
Why so many actuators on the DM?
Yeah, it's just to see how much we can correct. And you'll see that this is how large an area that we can cover. They call it dark hole. So here's a star surrounding, you don't know where the planet is necessarily. So you want that area to be as large as you can. In this experiment that I'm going to show you, we have one deformable mirror. So we could create a dark zone or dark hole that's a D shape because of that. In the next flight, we'll have another one, so we'll get it more or less circular.
So you got a table at the four with 4 different missions that you've run.
So this is the first 2 of that, the rocket.
You have
The balloons are coming up.
but you have the Zynetics
Yes,
silicon carbide in there.
right.
Non-actuated.
That's right. This is just a,
With the DM that you have in the Zynetics product or?
no, it's Boston Micro Machines.
And what happened to your silicon carbide mirror? Like that continued on.
It's still around, we're talking about, how we could use that to get into trouble together.
Leo showed Leo stuff and its performance of the system changed with or without Leo.
We see, this is we have a Gregorian, which is essentially doing that stop part, right? But you'll see, we do use a Leo stop for the balloon experiment, where we need that. So you're right. This is the problem. I'm surrounded by optics experts. I grew up I was an electronics and communication engineer. And I teach physics. I don't know what I'm doing here.
Non-optics question.
Oh, good, thank you.
Easier to do a rocket versus a balloon to start.
Yeah, yeah, we worried about thermal problems when we said, and there's balloons that still are floating in air, so there is air above you. So the reason most people in the ground are using deformable mirrors is to correct for the atmospheric correction. So we said, well, if we go on a rocket, we don't have that problem. But we didn't think about it. It's sort of like we knew how to build rocket experiments. We have done this. Let's go do rocket. No, actually, we thought about it. But we thought that would be a, quote, easier problem, because at that time, it was thought that all you had to do is get to a contrast level of 10 to the minus 6. And so that changed dramatically. It's now with a lot more measurements, it's another 1,000 times worse. Okay, so this is now where the state of the art. This is the goal of what we would like to see. Here is a solar system. The sun is somewhere here, Venus, Jupiter, Earth. You'd like to take that image. And that's the goal for all those big flagship missions that NASA has. And if you could put a slit on the Earth, and you want to take a spectrum of that, and this is what it looks like. This is the wavelength in microns, and there are all these absorption lines for various species. You would like to get water, ozone, all the usual stuff that you're looking for life. The problem with any of these things is diffraction, right? You put something, you get an airy function. So how do you deal with this? Well, the dealing is, imagine that that's the star spectrum. Star's airy function, and the red one is the planet. And if you pick at the right place where the star falls off and the planet goes out, you get a contrast that's roughly about 10 to the minus 9. And that's sort of where the 10 to the minus 9 number comes. You take the ratios. For some cases, you get higher, 10 to the minus 7. And that is a cherry picking thing. And our goal was, is there one? Remember the original question, is there even one planet that we could see? There are suggestions that this target, Epsilon Eridani b, is one of the nearest one, about 3 parsecs away, has something like a Jupiter. Sounds like a great thing, but there's always the but. So this is how the figure of merit are shown. What's shown here is the contrast, and along the x-axis, the separation. So the big flagship mission, this is 2040 thing, LUVOA or HABEX. It's the name has changed to a Habitable World Observer. But their goal is to get down to about 10 to the minus 9, or even to get to the Earth, another order of magnitude, 10 to the minus 10 contrast, and at a separation of 1/10 of an arcsecond or smaller. So imagine these kind of challenges. And there is a when Hubble was built, they had a spare mirror. And using that, I think the military had that, and they gave it to NASA. And there is a new program, not new, a program called Roman. It's now Roman. It is to have other names, other words after this. It's a mission that's going to fly, and it'll have a coronagraphic imager. So it's the same kind of thing. That's the CGI, and it's supposed to fly next year. And it's trying to get to about the same kind of number, a few times 10 to the minus 9, or close to 10 to the minus 8, at about 5 times farther. And in the same scale, what we're trying to do is this, even farther out. and trying to do it in a suborbital way. So the way we started looking at this is, we'll develop all the systems that are necessary and validate them all in one place. And our research group, as I was telling somebody, could fit inside one of these tables with few chairs left over. So we're very small, and we work with NASA for providing us with some components, and we do some of the others. And in this case, there are two techniques that have been talked about. One is formation flying two satellites. One satellite puts up a thumb that blocks the light. And say, it's of this shape, so the diffraction effects are minimized. But the challenge is you need another satellite that looks at the star as it comes. The light comes from behind this occulter. This thing has all the problems that we're talking about, plus flying with another. And Kepler's law said if you're farther away, you move slower than the one that's closer. So there are all these things. We thought that we have control problem. This is probably 10 times worse of control problem. Another one, so this is called external coronagraph, because the thing that's doing the blocking of creating this, the corona, that's how the name came to solar corona. And the other one is the internal coronagraph, where that's your primary mirror, like a James Webb. And then the entire coronagraph, the whole thing is inside. And there are many versions of this coronagraph that have been developed. And I'll skip this for now, but I'll come back to this figure later when we try to describe ours. There are many. The one that we use is called Vector Vortex Coronagraph, and I can understand individual words. Don't ask me to explain it optically. But what our goal is much simpler. We're trying to image something like an asteroid belt. And that's because it's much extended, much bigger in the sky, and compared to a planet. So if we could do that, we'll be able to demonstrate all the systems that we need for a more difficult problem. So our goal is that we have a field of view that goes from 0.5 arcsecond to 2 arcsecond. And our goal is to demonstrate that we could do a contrast level of 10⁻⁷. So that's the goal. And the way our platform is this. It's a balloon. It's the size of a football field. When it's fully inflated, we have hanging from that about 300 feet lower, 100 meters, is a payload. It's a gondola. So, if you look at the vertical, when we launch it, it looks like that. And then this red and white thing is the parachute. So when we're done with our work, or if the wind is taking us to some places where we shouldn't go, they pop it and the parachute opens to come down and we recover it. So that's how we're doing it. Now imagine when the rocket was moving roughly 3 kilometers a second and slows down, there is one kind of control problem. Here, the challenge is the wind blows you wherever the wind takes, unpredictable. And this thing swings like a pendulum. And also it has a twisting motion. All of those things are absent in an orbital platform. So there are certain things we could do, which is build and recover it and fix our mistakes. But the price we pay are all of this other complexity. And oops. So this is the rest of the part. And those of you with better eyesight than me, you can sort of see this. This is roughly about the size of a small car or a van, about I think it's 200 some inches, so it's 12 feet or so. This whole thing that hangs from the balloon is roughly about 6,000 pounds. So you're flying a small school bus, right? And it's an astronomical instrument. You have to now, this thing is doing whatever it's doing, and you have to point to an astronomical target, to some number of milliarcsecond. If you get to 1 milliarcsecond, that's what James Webb does. And that's where there are no disturbance torques. So that's sort of the challenge, and we're trying to do that. Now going backwards. So this is what the details of the instrument looks like. In here sits our primary mirror. This is where the secondary mirror is. That's a star tracker that gives NASA an idea of where we're pointed. And this gimbal structure is the one that NASA controls. So that points us to an arcsecond, or a little better than an arcsecond. And then from there, we take over. And this box is the coronagraph that we flew. And so if you want to look at the optical path, this is the primary mirror. So light comes this way. It's an off-axis parabola. The secondary sits on the hexapod. So now we have the luxury of making some changes or pointing corrections during flight. And the coronagraph sits in here. I'll show you the details. Everything mounts on this hub. And it's very well balanced. It's so well balanced, you could just move this 6,000, or in this case, 2,000 pound experiment with your finger. So it's very well done, and that's done through all these weights, and the electronics sits in the back. So the first thing we did was, got a slightly larger primary mirror. So we are using now a 60 centimeter diameter off-axis parabola, full thickness, so that's this glass. And they are mounted by 27 pucks at the back, and then it's a wiffle tree. So there is no pressure to warp it. And for the secondary, we use a physics instruments in a hexapod. And all of these things, we did it ourselves. This is in our lab. Our mechanical engineer, Jason, designed it, and we put it together. The first time, we're all worried, with this, glue that we got with this hole. Fortunately, it did, and we flew it twice, and it worked. And so that's the picture of the mirror looking at the truss structure, which is the optical bench. And it's an aluminum structure. It has to be lightweight. Aluminum has a thermal problem, but we couldn't afford carbon fiber at this time. So next flight, maybe. So now, how do we do this coronagraph part and wavefront control? So we do have adaptive optics. We have two sets. One has 97 elements that can move very fast. And then we have 1,000 element that's slower. And the 97 element has a larger stroke. This one has a smaller. So it's this woofer tweeter type arrangement. So this is the Boston Micro Machines one, and I'll show you the other. So basically, the idea is your wavefront coming through the telescope, and even though you're above most of the atmosphere, there is still some atmospheric distortion, but mostly the optics, our own alignment. When we launch these balloons, we launch early in the morning, so about 7 or so. And this thing takes 2 hours to get up to the altitude, and we go about 120,000 feet, 40 some kilometers. And we stay up there all day. And then after the sun goes down, we start taking data. So we have the luxury of now looking at some bright stars like Vega and others to do alignments and so forth during the daytime. So that's what we do. And the coronagraph is it's a brilliant idea, whoever came up with it. If you look at it, you can see through it. It's like a slide, but it's two slides encapsulating an LCD structure. And what they do is they put a ramp type phase in there by arranging the what do you call these things and liquid crystal, the fiber, I guess. It's not the fiber, but it's I cannot saying the word correctly.
Orientation.
Yeah, but there's a term somebody is anyway. I'm missing the word. And so what happens is if your light comes to the center of this, it turns that into, it blows it up, it turns that into a large circle. If it's off of that, the center, it goes through. So imagine what that does. If we put the star at the center of it, it becomes a ring. And you can put a Leo stop there to get rid of the starlight. And if you do that, inside that circle, you have a dark zone. And this is, there are many different styles. And so we use that and it works beautifully. So the way then this works is in here, the light comes through, there is a deformable mirror to correct the wavefront to as much as we can, couple of quarter wave plate, polarizers. And then this is where this, what they call the Vector Vortex Coronagraph is, and then comes out and this is sort of what happens. Once it goes through the vortex, you get this eclipse, so to speak. And that's the star, and you put a Leo stop type thing, a stop there, not Leo stop, but and that's how it works. So, and whoa. And that's a photograph of this device. Our colleagues at JPL uses it. There are many other types of coronagraph. This is a small, simple one. Doesn't have all those other optics that I showed with the visible nulling coronagraph. There are different types, but this is the one that we are using. This is the one that's planned for the Roman that is supposed to launch next year. I'm going backwards. So again, in here, we could do various things. So we have this deformable mirror. We could use that to look at the what's coming to the VVC, I guess. And then here is what we see coming in. This is what we see after the coronagraph, the vortex, and then we at the end is where the science camera is going to be. We looked at the surface problems, so we measured them. We had to correct. We also have the electric field that we need to measure. So there are all these details. I wish I could give you more, and there are some obligatory equations. So I wouldn't want to talk about that. I'm just going to show you the results. So in this panel, I'm going to show you the commands that we give to individual pixels of the deformable mirror, so individual mirror element. This shows that the optical system has problems. It's not perfect, so we'll try to correct it. And then the green part is where the science data shows up. So in here, it's a iterative thing. So that's now 4th iteration, and these are real commands that goes to the deformable mirror, and you'll start noticing things change as we go to more and more. And you can start seeing things are getting corrected. And over there, for the first time, you now see that this half of the science field of view is getting darker compared to the rest. And in here, we list the contrast level that we're achieving. So that's the key. We need to get down to 10 to the minus 7-ish. And this is now in the lab. So that this has happened in the last couple of months. So we're getting now about 10 to the minus 8 raw contrast. And that's a very good number because we're not using a laser. It's got a real light. So it has a bandwidth of about 20%, so plus and minus 10%. So we're going to collect a lot more data than at a single wavelength. So this is sort of the principle, and this is the optics that we used for our first flight. So the entire optics fits on a 2 feet by 4 feet optical bench that we use, just what you use in the lab, but we asked to make it out of carbon fiber. So the light from the telescope comes, we take, as I said, part of the light we use for fine pointing. The Vector Vortex Coronagraph goes in here. There are various other optics in there. And for our first flight, we took the null light and take different components with dichroics to see if we could get multiple colors. So this is what it looks like. And when we put everything together, it sort of looks like that. And again, this is all built in the lab, in our lab here. And this is the board that we, the carbon fiber optical bench that we got. There are cables everywhere. It's terrible. And metal, heavy. And then there are different types of wavefront control we had. One, we had this multi-element, about 100 element Shack-Hartman to give a part of it. And then we use a reflective Leo stop. So we use that. And then let me show you the results. That's more fun than looking at all the Zernicke's and stuff. So this is lab data. And so we see this pupil camera. That's the low order wavefront sensor from the Shack-Hartman that feeds to the hexapod. And what you see here, we look at this, and in here the command, so to speak, we give to the hexapod to adjust. And this is where we're going to get the wavefront, after some iterations, a reasonable image. So these are the kinds of stuff we're doing all the time in the lab to get things in a reasonable way. And there are too many systems, but what we get here is we have, these are our data. And on the right-hand side, we show some simulation of what our requirements are in terms of pointing. WASP is the NASA system called Wallops arc-second pointer. That's in NASA Wallops flight facility. And these are the data. So we have gotten very good, but we still need to do a little better. So we have a list of what we need to do. All this stuff in color are a lot more difficult to do on a balloon than you do in space. But nonetheless, we got this ready and we flew it. We have these 2 deformable mirror systems. This is a Boston Micro Machines. We got a custom controller got made. The ones that we flew on a rocket was like a, dorm refrigerator size electronics to drive this thing. And then this is the other one. This is a French company called Alpeo. They have a different technology that we used, or they use. So this is where finally it gets all put in here. And inside it is this, it's sort of like working on Sistine Chapel. And then we have this little tank where we put the chronograph and related electronics, close it and do a thermal test, mostly a vacuum test, but mostly when we launch at balloon altitude, the temperature is roughly about -50 C. So we have to make sure that, the ambient temperature on the ground, and when it goes over there, we can handle all of that. And so this is what the fully assembled thing looks like in our lab. So primary mirror in here, the secondary is there, chronograph, and the rest of the electronics. So we put it together and then put it on a FedEx truck. They take it there. They unpack it at the NASA facility where they have a lot larger space. But this is now the morning of the launch. We roll out at 5 a.m. This is our experiment. This is where it's going to hang it from. It's a huge truck that takes it out there. And so this is what, when we get ready to launch, our payload, and the gondola is right here, and the balloon is getting filled up there. And what happens is, as the balloon, they don't completely inflate it, they just put a little bubble in there and let it go. As the balloon goes up, the guy who drives this thing has to come really underneath it and then let it go. Otherwise, bad things have happened in the past. So. Much softer launch than a rocket. Don't have to worry about it. So we did that. And then this is our first flight. We launched from Fort Sumner. The wind for it, when we launched, takes a little bit to the east and then flies, over all of these. And I'm surprised that they didn't cut us down when we were going over Albuquerque. They used to launch from Texas, but then that launch site got too many oil fields nearby, so we can't do that. But then finally, these guys, are monitoring the weather very well, and then, they cut us down, and we got about 20-hour flight, and we pointed to various targets during the day and night. Didn't get the debris disk yet, but made some progress. And this is it's a video. We're now pointing at a target, and you can see street lights here, or city lights down there. And the reason I know it's a video is there's a meteor that just went by. So let me show it to you one more time. Oh, the time is not changing, is it? No. I'll do it one more time. Every time I say it, I want to say it again. So you can see that, we have done something where it is a real astronomical observatory. We're putting it in air where there's all this wind and other things. But thank goodness for NASA, they gave us 1 arc-second pointing, and then we did something with that. And then when they cut it down, this is how it came back. This is our crush pads. all those Amazon boxes, I guess. And the good news is it came back, in a very good condition, landed on a flat land, not on trees or anybody's house. God forbid cows, we had to worry about those in rocket days. So we could have launched again. And so to give you ideas of all the things that we did, we had a list of targets that we wanted to do, and we have demonstrated all of those using this flight. And this is the showing that we moved the deformable mirror, we can correct things and so forth. So that was in 2019. We went back again to launch in 2021. All these other problems, too much low altitude winds. So we stayed there for 6 weeks and couldn't launch. And so then finally we went there in 2022. And now again we launched. So because of the wind direction, now we're launching from a different side. The photos were taken from the same angle. Let me move to the next one. That's better. The camera, this is now looking at the camera on the payload. And so now you can see it's still being held by that, what they call Big Bob or something like that. And then it'll let go. You can see it on the shadow, it's still being held there. And when it just comes underneath, it'll let it go there. And so that's how the launch happens. And the usual stuff. And that thing that just came down, that killed an experiment in the past. So they have figured out how to not do that. It's a metal collar that holds it. So anyway.
How do they control the rotation?
They have motors.
It's like a reaction wheel? Or
They
something
have
that's
reaction
actually-
wheels for the thing, for the pointing. But this thing that you're talking about is just a regular. Yeah. And in this case, we again launched from the same place, and it came back, and it was getting too close to the White Sands missile range. They have no sense of humor. What can I say? So they cut us down, but there are a few more things that we achieved. These are, yaw and pitch positioning. So we're trying to see how well we can point, but this is now flight data on the sky. These are the deformable mirrors, and we're creating a dark hole. Nothing that has been bolted down to a lab has ever done. And so we did this. It's roughly about 4 times 10⁻⁶ on sky with all of those. And it was important enough that the director of astrophysics at NASA showed it at the American Astronomical Society meeting as a highlight of the work. So this is what we got in flight, and people have done much better than this in the lab, and we were grateful that we got some really dedicated, smart people who have been doing this. And we got 4 flights, and we already learned quite a bit with each flight. So to talk about what we learned from the balloon flights, all the things that are shown in red are new, first time used. But after doing all of that, we got a 1 milliarcsecond fine pointing. And as I said, that's the James Webb fast pointing. And we got this contrast in a large area in a broad band to about in the 1,000,000 to 1 level. At this point, one can do some, image processing to get that down and another 5 to 10 below. So those are picture C. That's a coronagraph. D is now funded as for debris disk. We have 2 flights coming up. I know it's getting late, but I promised some people that I was going to show you some other things that we do besides this. So the other stuff, this when the balloon, sorry.
No worries. I have a quick question. Why is this features? Why are you guys using a square structure instead of a tube or
Square,
a rectangular structure? The housing of the whole system?
I don't know why you're saying, but I'm guessing that it was easy to roll. It's covered with a sheet, thick plastic sheet. And so they figured that it might be, the engineer figured that it might be easier to do that. There was no reason other than what we could do quickly. And it's just a roller that we roll this thing, motorized, and when we launch, it's closed. When we get up to the altitude, we open it, and then before we come down, we close it again. So it's more of a dust cover than anything else. We could easily have made a motorized, other configuration, but anything else? I'm sorry, I was rushing to others. I have flown a balloon from India. Helium being expensive, they fill it with hydrogen. I was taking pictures pretty far away. It makes a lot of racket. But yeah, it can be done, and it's done pretty regularly. Indian balloon story is more, it goes well with stronger than water.
There's an anomaly that's sort of creeped in over the last few years, which is Starlink and some of the other mega constellations.
Right.
Is that you're staring?
Of course,
At what point in
yeah,
space do you actually get any aberrations?
It would be a problem. That's why a lot of the other astronomical things are higher up, right? L2 and whatever the JWST. In fact, you mentioned Starlink. That's a very interesting one. These are one-night flights that we're doing. NASA also has a thing called ultra long duration balloon, which it's a different type of balloon. These balloons go up and down with day and night, and they're called zero pressure. And those things are called super pressure, and they stay more or less at the same height. And they're launched from New Zealand and go around. And the idea, they have done things around the Antarctica, but that's only daytime. The thing that could launch from New Zealand could go quite a far distance. They have done like 45 days. And so you can imagine that's a poor man's satellite. And we could put meteor class optics in this, such a thing. And so we're thinking about that as well. And so because this is our, balloon experiment, and it's so heavy, we could design and build various things. We could do some technology development. So this is smaller than a 4-inch cube. Each 4-inch cube would be a 1 EU cubes set, and this is like 0.7. And what we did was we designed an optics that has 4 imaging panels, and we look out the window through that at this. And this was done because some of you may remember the Google X Prize thing. They were trying to go to the moon, and one of the finalists asked us if we could build something that they will take us. We did. Unfortunately, nobody was selected. We also do rockets. This is an image of a galaxy in the ultraviolet, 4 UV bands. And we also build a hyperspectral imager that's on the space station that's looking from roughly 80 nanometers to 140 nanometers and looks at the limb of the Earth and doing Earth's atmospheric monitoring. And the color is the data from this mission. And the line is, when I was a grad student, I had a instrument that was on an Air Force satellite that we used, got the data. So we know how that the things that we built locally work quite well, and the slit is in here. We also do other things. In this particular case, this is a LiDAR. It's a full waveform LiDAR. So what that means is it doesn't take the first return or the brightest return, but it takes multiple returns. And it's made for providing ground truth in a forest. So if you take an image of a forest, all you see are the leaves. And so you got to take an instrument like this to provide ground truth in various places. And the idea was to monitor how much carbon is sequestered in trees. And the best way to do that is go to a forest, chop down the tree, weigh it. That's how much carbon there is. But the second best would be to be able to image, and current technique is they go measure the diameter of some height, they call the diameter at breast height, and the height of the tree. Those two parameters give you a pretty good idea of how much carbon there is. And so we designed a LiDAR, so it's a X, Y, and we have the distance to every point. And it's a two color, so we could distinguish, these are fake color in this. We could distinguish between leaves and the woody material. So we have done that. We also do hyperspectral imaging. This particular thing can do spectra. Y-axis is the angle on the sky. In this particular case, that's in degrees, roughly about 40 degrees field of view. And it's got very high spectral resolution to the point that we can see an aurora under fully sunlit condition. So remember there was an aurora that happened recently? And the word was 20 years ago, there was a similar one. And 20 years ago, we saw, that's called Halloween aurora. It happened on October 30th. And so what you're seeing here is the daytime sky spectrum. These are the Fraunhofer lines, so the absorption line from the sun's atmosphere. Keep an eye around here. That's when I run the video, you'll see that an emission line show up. Oh, what did I do? So what happens is normally you don't see it because the emissions are faint enough that it gets absorbed by the Fraunhofer lines or other overwhelmed. But in this particular case, we could do a very high enough resolution. Normally to measure how much there is, we fit the solar spectrum and subtract and all that. But in this case, it was bright enough that we could see it. And this is 3 p.m. in October. The sun is still up. And another propaganda material I wanted to share with you. And then I'm being a bad guest. So we've been very fortunate that the Commonwealth of Massachusetts gave us some money to build a facility where we could do design a small CubeSat type mission, do mission operations, but more importantly, we could have all the test facilities. So we'll have shake tables, thermal vacuum, anechoic chamber for communication. So this is accessible to anybody. It'll be available to anyone who wants to use it. If you're a startup, you're a big company. So you'll notice that this is our consortium. We have the universities. There are some international partners. And here are some of the names you may recognize: Analog Devices, MITRE, BAE, Lockheed, and then some small companies. So when we wrote the proposal, the requirement for this program is we have to, for every money we take, we have to match with non-Massachusetts $1 for dollar. I'm not here asking for money. The day we took a nickel from the state, we matched. We already have all the matching funds. We would like you to come, use it, make it successful, because the goal here is to make Massachusetts. There are all kinds of spacefaring technologies here, but there is no single place where we, the nearest NASA facility is in Maryland. So we need to be able to develop this ecosystem, as they call it. So that's what we're doing. It's now getting built. This used to be the lab where Josh used to work. You wouldn't recognize it anymore. These are all the boxes came from an anechoic chamber. Every week I go, something different. There is the chamber outside thing got built. And the other thing is, you may have seen this announcement. There is an investment being made in Lowell. It's an $800 million investment, and it's called LINC. LINC is Lowell Innovation something corridor, and the phase 0 happens to have all this technology, but where we work in this building, and Draper announced, it's been announced that Draper is going to be one of the anchor tenants, and they're going to be in the same lab on the same floor with us. So there is a lot of excitement going on, and I hope we could work together. And this is my sort of request. Come, let's work together, make it successful. Whatever metric you use for success. So anyway, what I showed you are that we've been developing technologies and testing them and validating them in space. Hopefully, some of them will end up in major flight missions. So thank you.
Thank you very much. I want to open up to a couple questions.
It's late.
So maybe I'll ask. I want to.
So you had shown, like, after the Leo stock, you're trying to create this dark hole that has this very distinct, like, D shape.
Why?
Can you elaborate on that?
We only took half of, because it's a question of money at that point. Each of those deformable mirrors cost a couple $100,000 plus the controller. So we had money for only one, and we said, well, if we could make one work, we'll get another one to do the other half of the.
You would need an additional mirror.
Yeah, and we have that for the next flight. And this is 1,000 element. For the next flight, we're getting 2,000 elements. So because a lot of things we have done, and we could just copy them, NREs. You have.
Yeah, so on the first generations of the system that actually got flown on the rocket, it was designed at 10⁻⁶ contrast. You showed some of the pointing performance on it. I was wondering if there was any, say, imaging that was captured with it.
We didn't. We didn't.
Okay.
The chronograph part didn't work. So that's why we went with the now a simpler chronograph, which is this thing that looked like a slide rather than just full of optics.
Thank you.
What does the balloon launch cost?
Costs zero to us.
If I were to say I want to go for a ride.
If you want to go for, that ride, you may not want to go on this ride, because you will need a lot of protective things, because it goes up to 120,000 feet. If you want to go there, I think NASA does fly. If anybody come with a check, they will fly. And for the ultra long duration, because it's New Zealand, they have to take a lot of people there. I think I got the number and different numbers at different times, but a couple $1 million. And I'll leave it at couple, because couple is a fuzzy enough. that I don't know what the number you'll get today, if you ask them. That's why my number is kind of old.
It's just, there's a cost for the balloon, there's a cost for the helium, there's a cost for the service. I'm just wondering, it seems to me that's a lot cheaper than a rocket.
Oh, yeah, but rockets, because rockets have the first stage is salvage. Right? So they only built one stage, maybe two, that are new. So, and that they have a contract with Canadians where I've been told that $1 US buys a $3 Canadian or some such thing. No, I'm being serious. But they're comparable, but I don't know exactly how the costs come out to be. Launch cost probably is not the biggest expense. On the other hand, we don't know that because NASA gets that money straight from the headquarters, how much a rocket launch costs. I would guess similar. If they used to fly about 20 or so rockets, when I was young, now they fly about 5 or 6. So the prices have gone up. I'm sure.
When I was in school, I worked at Honeywell Radiation Centers. We made a Fourier transform interferometer, which they launched up in the Arctic. And they were interested in, they told us, measuring the spectra of the aurora. It sounded to me like a cover story. Why would the Air Force be interested in the spectra of the aurora?
And also, why such a high resolution? I don't know that, but I have built and flown such a thing. It's a Fizeau interferometer where I was trying to measure the line shape of hydrogen Lyman alpha. So 121.6 nanometer, right? What I was trying to do is the solar system moves through the interstellar space, and I wanted to measure the speed and the density of the material in the interplanetary medium, because it's dominated by the solar system, Earth's emission. So I wanted something that has a high spectral resolution, then I could get the Doppler shifted. So I could tell you a scientific reason for why you may want to do. I cannot tell you why Air Force did it. There was somebody.
If I can interrupt, I know they were setting up nuclear bombs. Certainly in 1962. I know specifics of some of those. I was working with the Air Force Base.
But does it
And
need
they also worked
the
with
high
holes in the
resolution?
ionosphere. That was work ongoing in the 80s and 90s. So you need to monitor that. So I'm not saying that maybe they actually did 100% in the aurora, but I think generally knowing a lot about what is there. It is part of the reason I know about the nuclear bombs is John Paulson of the Air Force Base, but then when he started nuclear, told them they shouldn't be doing that yet because he didn't know what was naturally within their belts at the time. They hadn't been characterized very well. So if you hadn't characterized them, how could you tell what you were doing or perturbing that you were seeing? But anyway, that's part of it. My guess is the figures, I really had a follow-up question to this in the cost. That cost though includes them monitoring you that whole time, right?
The time, yes,
Shooting you
people's
down
time.
and retrieval and everything. So there's a pretty big package there, not just cost of helium and balloon. And safety for, do we shoot you down
Yeah.
here? Do we monitor you over Albuquerque? So there's a huge package around that, I'm sure.
I think we have one more question.
Completely non-optical as well. Do they recover the envelope? Do they remotely deflate the envelope balloon?
Yeah, both of our payloads were recovered.
But the balloon envelope itself.
Oh, the balloon itself. I think sometimes they do. I don't know because frankly, we didn't care where the balloon went, so we didn't look for it. But I know that it comes down. Where it comes down, I don't know. But I do know that even payload came down on trees and things on a steep slope. So your comment, my thesis rocket was an extreme ultraviolet spectrograph. On that satellite, part of it was classified, other part was where we had. And it was STP 78-1. I can't forget that. But the interesting thing is, many years after this whole thing was done, I got a phone call saying, "Are you using your instrument?" No. Why? Well, you don't know. You will read it in Aviation Week. It was a target for a missile. It was the first, target. And indeed, I can't remember, but I have the cover page of Aviation Week. The missile was launched from an airplane and then took out that whole satellite. Yeah. So that's when we intentionally were the first to put, just that I know of, put debris in space, not the Chinese, which we all know about. That happened a lot recently. Anyway, sorry.
Any last questions before we call it quits? I don't, no, yeah, that's what, yeah, I didn't say anything. All right, well, let's thank our speaker again.
Thank you. Please come visit us. The food's not gonna be as good, but we have a brewery next door.